Welcome back. Remember how we said that JavaScript is a single-threaded language? But with the asynchronous ability, we're able to do things in the background. So that even though we have JavaScript that is just one thread, we're able to do these complex things and still have websites and programs that perform well. Because with the asynchronous model, these requests that take a long time don't block the main thread. But the thing is, where do they go? Where does the web API have this compute power to run these things? And the thing is, tasks in a web browser, for example, or even in Node, where we use something like fetch or set timeout or look into the database or read a file system in Node. These are still executed in threads. The thing is, this is hidden from us because often they are running on their own separate background threads outside of JavaScript. You see, when I create a new tab here, the browser creates one thread per tab so that I have an entire JavaScript call stack and memory heap in here every time on new tabs. And as soon as I close the tab, well, that thread dies and is gone. Now, on the main thread, let's say on this website, the JavaScript program that I'm running is on the main thread. But sometimes there's things that we need to do in the background. And the browser has something called web workers that work in the background for me that I don't really need to know about. But if there's something complicated that needs to happen that's outside of my control, they take care of it for me. By the way, remember this diagram where I talked about the idea of a single-threaded model? And Node.js became popular because even though it had this one thread, it was able to pass off things into the callback queue so that it never blocked this one single thread and it just passed things on to different things. Unlike the traditional model where any request that we would have towards a server, we would spawn a new thread, handle that, but because that would be blocked, we would have to spawn another thread for the next request. And if we ran out of threads, well, the request would have to wait for our thread pool to be available. And Node.js is able to do this because of something called worker threads. You see, in the background, although the limitation of the V8 JavaScript engine is this single-threaded model with one call stack, we can pass things off to something like libuv that is written in C++ to handle worker threads and multiple worker threads in the background for us. And just like that, on the browser, we also have this idea of a web worker. And a web worker is a JavaScript program running on a different thread in parallel to our main thread. Now, how can we create something like that? It's quite easy. We can just simply say variable worker equals new worker. And this worker, our window object, will have access to. And it can read from a JavaScript file, let's say worker.js file. Oh, make sure I spell that right. So we can spawn a new web worker and assign it to worker. And now in here, from this worker, we can actually do something called post message to post a message to another thread. So I can say, hello. And in a different thread, such as, let's say, the main thread, I can just say add event listener and then just listen to a message. And if we get a message, like post message, well, we can take that data from one worker into our own thread. Now, most of the time, you won't be working with web workers. I just want to show you that they do exist in the background. The main takeaway is that web worker is a JavaScript program running on a different thread alongside our main thread. just like a browser creates a new thread for us when I create new tabs on our program. Now, keep in mind that these web workers communicate through these messages that I just showed you, but they don't really have access to all the browser web APIs. Like, they don't have access to Windows or Document Object, but they do have some abilities like using set timeout, location, or navigator. But luckily for us, on the browser, that's taking care of it for us, right? Using things like fetch on the browser. We don't need to worry about different threads working on something else. We just call it using this facade function. And it's a facade because underneath the hood, it calls on to the web API and says, hey, web API, I have something for you. Can you take care of it for us? Which is really nice. It's out of our hands. What about in Node? What happens in Node? Well, as you saw, we have worker threads. When we do something like reading from the file system, in the background, Node does these things for you. Reading from a database, Node does it for you. So we don't really need to worry about having to create our own threads, which is really, really nice. It makes our programs simple. Now, I want to finish off this video with this diagram that I actually got from Stack Overflow, and I think is absolutely great. This shows the difference between two terms that are really, really common, but also confusing. The idea of concurrency and parallelism. You see, if we ran this first program, where we only have a single core CPU on our computer, what the computer would be doing is it'll be working on one thread. As soon as it's done with that thread or has a bit of time, a bit of pause, it can switch to the next thread and work on something there. And then, back to thread 1 because we have more work to do, and then back to thread 2. It can switch back and forth between these two threads, but only allowing one thread to run at a time because we have a single core CPU. That is, one CPU can do work. So the best way to think about it is just like this man over here, eating. In a single threaded model, you just have one mouth to eat these things. One mouth means a CPU. But you have two hands, right? So you can grab something from the plate, let's say an apple, and bring that to your mouth. And once you're done with that, you can grab another hand with, let's say, a banana and grab that and bring it towards your mouth. And that is what concurrency is. Concurrency is something that we can achieve in JavaScript, right? We're using concurrency when we work on our single-threaded JavaScript, but in the background, we use Node or web browsers to actually allow us to do things in the background on different threads so that we can accomplish things. But we can only do those once our main call stack is done with our work. And then we have this idea of concurrency as well as parallelism. And that can only happen when we have things like multi-core CPUs. That is, many CPUs, many more mouths than just one. And this is kind of like that man having two mouths or having two people eat food with two hands each. If we ran this program, the multi-core CPU would allow us to execute threads at the same time because each one would be on a different CPU. So we'd be able to run these threads in parallel, side by side, at the exact same time. How cool is that? Now, when it comes to parallelism and JavaScript, you can't really do that, can you? It's not really built into the language. But there is a way to achieve something like this on, let's say, something like Node. You see, Node was built for simplicity, but if you have, let's say, 4 CPUs on your computer or server, then you can run that Node instance on all those 4 CPUs. So how do we create more of these processes that can run on multiple cores? Well, in Node, we can do something like spawn, and there's 3 other ways of doing this, different ways of doing this, but we'll just use spawn as a good example, and we'll just require the child process module that comes with Node, which will spawn a new process. And then we can just run this process by saying, let's just say git stuff. And if I run this, I'll generate a new process that I can run. Now, this is very advanced. You can read up on your own. The point of this video is just to show you the idea of concurrency and parallelism, the idea of threads, and how that works in our programming. And although JavaScript might be single-threaded, might have just one call stack, the beauty is in its restriction and simplicity, because this is really, really hard to manage. Parallelism is extremely difficult, especially when you have these two threads touching the same data. The fact that we have a single call stack in our program allows us to write really nice, clean code and have asynchronous events that happen, which I think makes things really, really fun to code and avoid some really, really strange bugs that might occur in a model like this. All right, this was a little bit beyond the scope of the course. I just wanted to throw it out there so you can go explore on your own if you're interested. As always, thanks for watching. I'll see you in the next one.